Okay, so now let's get on to the next lecture, which is lecture 16. So in the previous lecture, we talked about packing in solids, basically metallic solids. We looked at how do atoms pack in these materials, what is the atomic packing factor, what is the coordination number, and we also looked at, in the beginning we looked at the other two type of lattices, which are BCC and simple cubic lattices, which are not close packed. Okay, close packed structures are FCC and HCP. BCC and simple cubic are non-close packed structures, but they do have, we do have certain metals which follow those structures. So as a result, we need to know about them. So now we will talk about a new topic in this metallic materials, which is essentially interstices. Interstices is basically an interstice is a void. Okay, we can see that since atoms are spherical in nature, they don't completely, they do fill the space, but there are voids which are empty, there are empty spaces within the lattice. So as a result, so for example, if you see this particular kind of arrangement, okay, you can see I can put an atom here on top, the next layer goes here, all are same atoms. The red is only for the sake of illustration, but you can see that within this body, which is made by 3 atoms at the bottom and 1 atom on the top, this body is called as, if all the atoms were of same sizes, I can create a body by connecting the centers of all the 4 atoms. Okay, 3 at the bottom, 1 at the top. This body is called as a tetrahedra. So basically a tetrahedra is something like that. You have a, so I'll have to draw a little oblique shape. This is sort of a tetrahedra where one atom is here, another atom is here, another atom is here, another atom is here, and you have certain space lying at the center of the tetrahedra. So the space which is available at the center of tetrahedra, you can fit a certain size of atom there. So obviously that atom is very small. So the size of atom which can fit in the empty space within the tetrahedron is called as R tet, let us say, and this R tet is much smaller than R of the radius of the host atom. Okay, so we'll see what this size is. So this size where you can make a smaller atom sit here, this is called as the space in which an atom sit. This is called as a tetrahedral void. Okay, so you have a tetrahedral void here. Similarly, you can have tetrahedral void underneath. So various, so as long as you have this 4 atom body which is symmetric in nature, which is a regular tetrahedron, you will have a tetrahedral void. Tetrahedra doesn't need to be regular. We will see in certain cases tetrahedra is not regular, but as long as it has a shape of a, it is. So you can see that how many sides does it have? It has 3 on the top and 3 at the bottom, right? So it has total of 6 sides. So as long as you have 6 sides body, which looks like a tetrahedra, it can be tetrahedra. It doesn't need to be regular tetrahedra. In this case, it's it's let's say 2R, 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 but in some other case, all the dimensions may not be equal. So we'll need to be careful about it. But in FCC and HCP structures, it's a regular tetrahedron. So this is the tetrahedral void. Okay. Then you might have something called as an octahedral void. So here in this case, you can see that this has 6 edges and 4 faces. In case of octahedra is a body like that. Connect an edge here, you connect the edge there, you connect the edge here, you connect the edge there. It has an apex here. So it has 8 faces and 12 edges, okay, and 6 corners. And in this case, how many corners you had? You had 4 corners, okay. So this is the description. Now this octahedra can be found in a ABC or AB kind of packing. The configuration looks something like that. So you have an atom sitting here, the next layer goes there, and the next layer which comes on top does not need to go exactly on top of A, it can go to C. So you will have this kind of, so this guy which is sitting at the center is surrounding by 3 at the bottom and 3 on top. It has 6 possibility of 6 coordination. So this small atom, so this should be small actually, I have drawn it bigger, but this should be small. So one bit, so this is basically an octahedral atom sitting in octahedral site. So this is my A layer, this is my B layer. Between the A and B layer I have an octahedral void. How do you visualize this? You can visualize this, so this octahedra is a little tricky to visualize. So let me show you first the Fcc structure. It is easy to visualize in case of Fcc structure, it is difficult to visualize in case of HCP structure. Okay. The octahedral void in this case is made by connecting the one atom will be here as well. You connect these faces, this is the octahedral void in case of a Fcc structure, and the location of octahedral void is half. Okay. To find out the size, which we can do in a short while. So this is the octahedral void that you can form at half position. Are there any other octahedral voids present in the structure? No, not on surfaces, on edges. So this will be one octahedral void, this is another octahedral void. So how do you form an octahedra here? So because you can always, if I use a different color, this is, you will have an atom here sitting here, somewhere here in the neighboring unit cell, right? This will connect to that. You can connect this to the atom at the face center, and the one at the bottom face will also be there, right? So this will again connect to, so this will be octahedral void. So all the edges will also be octahedral, center of the edges will be octahedral void locations. So the octahedral voids in case of Fcc are located at half, 0 0, 0 half and 0 half 0 and 0 0 half. Okay. And since each edge is shared by 4 unit cells, As a result, since there are 12 edges, so this will contribute to 1, these will contribute to 1 by 4 into 12, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But since each is shared by 4 unit cells, 12 divided by 4 is equal to 3. So, you have total of 4 octahedral voids within a Fcc unit cell. So, and tetrahedral void on the other hand in Fcc structure lies at okay. Tetrahedral void lies at the position which I am going to show you now. If you connect this atom with an atom here, an atom here, and with an atom here, and if you connect these places with each other, this will make a regular tetrahedra. Okay. Similarly, if you connect this atom with this atom, and this atom, and if you connect them with each other, you will make a tetrahedra. So, these are basically tetrahedral voids. They are located along the body diagonal. So, this position is 1 by 4, 1 by 4, 1 by 4 type. Okay. So, tetrahedral voids, there are, so you have 4 body diagonals and you have 2 on the near the each corner. So, as a result you have 8 tetrahedral void in a Fcc unit cell. Locations are 1 by 4, 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 3 by 4, what else? 1 by 4, 3 by 4, 1 by 4, and 3 by 4, 1 by 4, and then you will have 1 by 4, 3 by 4, 3 by 4, then you will have 3 by 4, 1 by 4, 3 by 4, and then you will have 3 by 4, 3 by 4, 1 by 4, and then you will have 3 by 4, 3 by 4. These are the 8 locations that you will have. So, in a Fcc unit cell, octahedral voids are 4 per unit cell or 1 per atom, because there are 4 atoms in Fcc unit cell, right. Tetrahedral voids are 8 per unit cell or 2 per atom. Same is the case with HCP. Okay. Same is the case with HCP, because both are close packed structures, they have same, but this is just the arrangement is different. So, for example, for Fcc, HCP, a tetrahedral void this is one atom, this is one atom, this is one atom, this is another one. Okay. And now if I just make sort of a within this somewhere you have this atom sitting. So, one of the tetrahedra which is made is this, sorry. So this is one of the tetrahedra that you have. Another tetrahedra of course is this. So this is one tetrahedral void, this is another tetrahedral void. So what is the location of tetrahedral void in this case? This tetrahedral void is at 1 by 3, 2 by 3, this is at half, this is half. What is this location? 1 by 4. This is at 1 by 3, 2 by 3 and 3 by 4. Now, but there are only 2 tetrahedral voids here. Where are the other 2 tetrahedral voids? Now, if you look at the top view of a hexagonal unit cell, this is the top view of hexagonal unit cell. So, the unit cell is okay. You have one atom sitting and let us say if this is my first unit cell, okay, I am saying that one atom is sitting here, the second atom got to be sitting here and the third atom is got to be sitting somewhere here. So, you can see that these 3 give you one tetrahedral void, but remember these atoms also share the tetrahedral voids on the sides. They are sharing the tetrahedral void of the neighboring unit cell. So, those 2 neighboring unit cells contribute to the tetrahedral void of this unit cell. So, as a result you have, because of sharing with the neighbors, just like in FCC, right, because of sharing with neighboring cells, we have 4 tetrahedral voids per unit cell, and each unit cell has 2 atoms. As a result, it is 2 per atom. Similarly, octahedral void is 2 per unit cell or 1 per atom. So, let me show you how the octahedral void looks like. Let me show you. It is a little difficult to draw. So, this is how the octahedral void looks like in FCC. So, this is the bottom one is the first layer, the lighter one is the second layer, the top layer. So, you can see 3 atoms at the bottom, 3 atoms on the top, between them there is a octahedral void. So, this octahedra is a bit tilted octahedra. So, the first 2 atoms here, so let me just now draw. So, this is the square shaped body, this one, alright, and this is one apex and this is second apex, okay. So, if you connect now, you connect it here, and of course, you can connect, you will have to connect there as well, and then you connect to here and you connect to here. So, it is octahedra which is a tilted octahedra. It does not look like as if it is a standing octahedra, it is a tilted octahedra within the unit cell, okay, right. So, this is how the octahedras are arranged. You can see on the right, these are the various octahedras within the hexagonal unit cell. So, you will have total of 2 octahedras per unit cell. So, now these octahedral and tetrahedral voids are of lot of importance. So now we need to consider what is the size of these octahedral and tetrahedral voids. So let us take the example of Fcc unit cell. Because what will go in them is determined quite a lot, quite strongly by the size of this size of the atom, which is dependent on the size of the octahedral void. So let us say we have these atoms at various locations. Okay, one atom here, another here, another here, and another here. We are saying that my octahedra is, sorry, this is my octahedral void. Okay, the atom which goes in there is somewhere there. Now, if you, of course, the atoms are not touching here. If you make a 2D view of this, so what is this length? This is A, very good. And these lengths are A root 2 by 2. There is nothing but phase diagonal, right? So the size of, let us say, the size of atom which fits in the octahedral interstices is equal to or oct. And so I know from this is that this is equal to, then will become, so since these atoms are not touching each other, you will have situation like this. You will have a atom sitting here, smaller atom here, you will have an atom here. Okay. So you can say that R oct plus two R, let us say just R is equal to A. And what is the relation with respect to R and A? We know that these two atoms touch each other, right? So, or if you, so this is the sort of the 1-1-1 plane. So, if that is the case, then the distance between this and that atom, the distance between this and that atom is nothing but A divided by root 2 by 2. This is equal to 2R. So I can now find so there is a relation between, so I can write this A to be equal to 2 root 2 into R. So R oct plus 2R is equal to, okay, so R oct is equal to 2 root 2 minus 2 into R, and this will work out to be so this is how you will determine this 2R, yeah, this is 2R, yeah, this is the mistake that we have made. So this is 2, so 2 2's will cancel each other. So this will be R oct will be equal to root 2 minus 1 R. Root 2 is 1.414, right? So this will be 0.414 R. Okay. So that's what I was wondering, that the numbers have gone somewhere wrong. So this is 2R oct, because remember this is 2 of R, which is diameter. So 2R oct plus 2R is equal to A, and we know that A root 2 by divided by 2 is equal to 2R by the geometrical relationship of Fcc unit cell. Just replace A in terms of R, and what you get is R oct. So the maximum size of the atom that can fit an octahedral void is 0.414 of the radius of the host lattice, and the same is true about hexagonal lattice as well. Similarly, if you now need to find out the size of octahedral atom, in case of HCP it's easier because the atom sits at in case of tetrahedral void, since it's at 1 by 4, 1 by 4, 1 by 4, the distance between this point and the apex is, so let us say if this is the tetrahedra, I'll probably do it on the next page. So I'll just draw these three atoms, okay. The one at the center. Tetrahedra is made by connecting this atom with this atom and this atom. This is tetrahedra, alright. Our atom is sitting somewhere here, okay. This location is 1 by 4, 1 by 4, 1 by 4 type, okay, and this connects the body diagonal. So if this is O, this is A, the distance OA is, diagonal is A root 3, and this will be 1 by 4 of A root 3. So if you have an atom here which is small atom, which is a tetrahedral atom, which does not distort the tetrahedra, it just sits in there snugly without distorting the tetrahedra. So then this R of tetrahedral atom plus R of host is equal to A root 3 divided by 4. And what is A in terms of R? Root 3 divided by 4 into, in case of FCC we know that 4R is equal to root 2 A. So, A is equal to 2 root 2 R. So, R tet plus R is equal to root 3 by 4. So, sorry, why am I doing it again? So, I just substitute this by in this equation as 2 root 2 R, okay. So, this will be R tet. So, R tet plus R is equal to root 3 by 2 into R. So, as a result you can write this R tet to be equal to, if you just work this out, this will be nothing but is equal to, so R tet will be equal to R into root 3 by root 2 minus 1, which is nothing but 1.732 divided by 1.414 minus 1, okay. So, you can see that this is more than, so this will be 0.225 R, okay. So, this is the maximum size of atom that can fit in a tetrahedral void without distorting the tetrahedral void, okay. So, the similar size of atom, you can also do tetrahedral void calculation just by drawing a tetrahedra. And so, if you just make the simple picture of tetrahedra, so this is your tetrahedra for example, and the atom which will fit somewhere here at the center of the tetrahedra, these are all touching atoms there. So, just like you do the calculation for C by A, you can do the simple calculation of, so that if you remember we worked out two distances CV and CF, okay. So, you just have to work out this distance from the center to center. So, this distance is equal to, let us say if this is A, this is B, AB is equal to R plus R tet. So, you need to work out A in terms of, AB in terms of small r, using the geometrical methods of a simple tetrahedron. So, this will again give you the same relation. Octahedral void remains the same, and so in case of HCP also, R tet is equal to 0.225 R and R oct is equal to 0.414 R. Things are not same. Now, this is about the closed pack structures. Things are not same in case of BCC. In case of BCC, since BCC is it's not a closed pack structure, but it does have voids. You know, it's not a closed pack structure. As a result, it has voids. You have one atom here, 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 and one here. It has voids, but they are all distorted voids. So, for example, the octahedral voids in case of BCC, these are the octahedral voids. So, this is the octahedral void, but this is not a regular octahedra because all the sides are not equal. This is A root 3 divided by 2 and this is A. As a result, it is not a regular octahedra. Okay. So, these kind of octahedral voids are present in BCC. What is the tetrahedral void? The tetrahedral void is basically, if I draw another atom on this side, then tetrahedra drawing by different color maybe. Try this color. So, this is a tetrahedra. This is a tetrahedra. Center of this will be tetrahedral void, but this is again a irregular tetrahedra because you can see that this length is A, this length is A root 3 divided by 2. So, as a result, sizes are not the same. So, I will leave it to you as a homework that how many octahedral and tetrahedral voids in BCC, locations, determine the exact location in terms of coordinates, and the size of these voids. In BCC. So, but it is a fairly straightforward thing to work out because you remember that you have to take the shortest size, you do not have to take the longest size. There will be two sizes, one, so depending upon which distance you take, there will be long and short. The smallest that can fit is the given by the shortest. Okay. So, these are the octahedral and tetrahedral voids which are present in metallic structures. And these voids are useful because the impurities go in them, because nothing is pure in nature. Steel contains carbon, and carbon is a smaller atom, it goes to interstices, and that makes the steel stronger than pure iron. So, it is good to know about these interstices. These interstices are also important when we consider the ionic solids, because in ionic solids anions are bigger, cations are smaller, cations occupy the interstitial sites. So, that is where the knowledge of these interstices is very useful. So, in the next lecture we will talk about the solid solutions and alloys of metals, and once we finish the metal part we will move on to covalent solids and ionic solids. Okay. So, we have spent quite a bit of time on packing of solids, the packing fraction, coordination number, and then the interstices, and this has formed the basis of studying the substitutional interstitial solid solutions and alloys in metallic structures. Okay. Finish here. Thank you.